Thank you. It's a great pleasure to be here. Initially, I had a subtitle to this talk, Physics-Inspired Algorithms, Hamiltonian Monte Carlo. But since I have a little bit more time, I'll try to present one more example of Langevin dynamics. And I know this meeting is about statistical physics and machine learning. This talk is more about physics of statistical machine learning. So, So let me just set up the stage of what kind of problems are we interested in. So in machine learning and optimization and even theoretical computer science, where I come from, the problem is this kind of problem shows up quite often, that you're given access to some function, f, which is defined, its domain is all of RD or maybe some subset of RD, and think of D as large. So this is a high dimensional setting, and this is a real valued function. And one of the goals is to find this theta which minimizes the value of the function. Okay? This is the optimization setting. A related sampling setting is the following, that instead of finding the theta which minimizes the value of this function, you look at the density function in this space RD corresponding to this function. So if you look at f, you look at e to the minus f, this gives rise to a measure at each point in RD. And what you would like to do is to sample a theta from this probability distribution. You can also add some constant or temperature or whatever here. I mean, that can be absorbed in f itself. So this thing is called the Gibbs distribution, and probably has many other names. The reason why I put a minus sign here is to make it consistent with the goal of minimizing f. You can already see that this density function favors points with smaller values of f. And yeah, so these are two fundamental problems which are driving many different areas. Sampling is often harder than optimization. And if it were up to many people who are doing deep learning today, they would be sampling. But I mean, this turns out to be a harder task. And this is what you end up doing when you're training a deep network or something like that. But I'm going to focus on both of these problems today. And one of the problems would be, the first part of the talk would be, and the bigger part of the talk would be about this. So let's set up some concrete example for you to have in mind, given that this is a machine learning workshop. So often, what happens is that you're given a large data set, where, for example, you have these images. So think of data points as these vectors xi's, and think of yi's as some kind of discrete labels which may be corresponding to their class. In this case, airplane, automobile, bird, cat, or whatever. And you have chosen some family of models with which you want to represent this data, and you're trying to learn the parameters of that model, which are captured by this vector theta. So it's a lot of parameters for a particular model. Want to be concrete, you can think of a deep network or even one single layer network or two layer network. This theta corresponds to all the weights on these edges. That's what you want to learn. And this L is what is called the loss function, which applies locally on each data point. So this is the kind of functions that arise a lot in machine learning. And you want to solve these problems for these kinds of functions. To be more concrete, here is one function which is called the logistic regression function. I'm not really a machine learning person, so I may be not saying the most popular name, but I know it as a logistic loss function. And yeah, we're going to talk a little bit about this function today. So it consists of, the task of either optimizing or sampling consists of as two facets. One is to develop methods which will give you something here. And the other, and sometimes harder and sometimes really hard and maybe not possible, is to give some kind of guarantees. You can give a method, but you may not be able to say when does it work, under what conditions on these data vectors, xi's, does the method work. And why do you need guarantees? Well, as theoreticians, you might just say, I like algorithms with guarantees, but there's a more effective reason for that. Often guarantees allow you to tune parameters, which is a big deal. Anybody who has tried to work in this area knows that tuning parameters can take a long, long time, and at least they give you some starting points. So that's really what comes with guarantees. So these two facets actually benefit from the physics viewpoint. And I'll give you some flavor of this in this talk. The first, developing methods, it's often useful to think of optimization or sampling as some kind of a particle moving on some landscape. So in the simplest possible setting, you can imagine that there is a particle, theta describes its position, and the position is changing at every time instant while taking some feedback from the function that you want to optimize. The function f somehow introduces a geometry and the particle is moving in that geometry. So you can think of it, and it's entirely up to you how you want to formulate the geometry, and there are many, many very clever ways. People who have done courses in optimization know gradient descent, Nesterov acceleration, mirror descent, interior point methods, ellipse. There are many, many different things you can do. But at least some of the more interesting ones, think of it more from a physics point of view. The second one, it's not maybe completely obvious. When you want to prove convergence time bounds or establish conditions on the input for which these methods work, you often search for some potential functions. These are all dynamical systems at the end of the day. And to prove convergence even locally, you're looking for some Lyapunov functions, and that also often is intertwined. If you have the right equations of motion, you may have invariants, and we're going to see some stuff here like energy or whatever that help you at least get started on proving things. So this is not to be taken very seriously. That's why the talk has the title Inspiration. These are not physics-directed algorithms. You think of this, if you're a mathematician or an optimization person, you would say, I don't really need to know the physics to prove things. And often it gets done that way as well, but it's helpful. And we are in an institute, which is, largely a physics institute, and I think it's apt for me to kind of give this viewpoint here. Okay, so this is a one-slide introduction. And now we're going to look at some specific problems and specific methods. And the first part of the talk, which I anticipate to be more than 2/3 of the talk, is Hamiltonian dynamics and sampling from. So we're going to talk about a sampling problem, but we're going to develop a method which is based on Hamiltonian dynamics. And just a little short story. 4 years ago, I knew nothing about this. And then Spenta, who's the founding director of this institute, he came to my office, and I was at EPFL at that time, and explained to me, and I looked at this with, I still look at those notes sometime to understand these Hamiltonian dynamics, Lagrangian dynamics, and so on. So that's the connection to this institute. That's why I came here to give a talk, and I'm glad Spenta is sitting here. listening to what I have to say. So what is the problem? This is the problem that we're going to talk about. So let me be a bit more precise about given access to this function. What does this even mean? So for this talk, it means that we have what is called a first order access to this function or a gradient access to this function, where if you give me a point x or theta, I can tell you what the value of f is, and I can also tell you the gradient of this function. Okay? So that's the computational model we are working in. And given this access to the function, my goal is to solve this problem, to output a point theta with probability distribution which is proportional to this density function. And let me just be at the very outset say that we will not be able to solve this problem exactly. We are not going to be able to sample from the exact distribution pi. If we were given infinite time, this would be possible. But because we want these algorithms to be fast, we'll have to stop at some point. And at that point, we will have some guarantee on how close the distribution that we sample from is to the distribution, which is the target distribution. Okay? So the traditional approach to sampling is what is one major approach to sampling is what is called Markov chain Monte Carlo along with Metropolis. And let me just kind of give you a very high level view of this. It's kind of like these iterative methods that I mentioned in my previous slide. So you at any given step in the algorithm, the kth step in the algorithm, you have some theta k. Now theta k in this case is some random point. By random I don't mean uniformly at random, but random means that it comes from some distribution, and the hope is that eventually, after a small number of iterations, theta, let's say after t iterations, theta t is very close, comes from a distribution which is very close to this pi, which you're looking for. Okay? So these MC-MC methods kind of do the following. So there is a proposal step where you say, okay, I'm at theta k, I look at what the value of the function is or what the gradient is, and I'm not being very specific about what exactly do you look at this. This is some input that you get from the function, and then you update your point. So you move to the new point. Theta k plus 1 is theta k plus something or minus something, but well, this thing could be minus. So one of the major problems in this is that since eventually I want this point to come from the distribution pi, I want this step, which for sure has to be randomized as well, because somewhere randomness has to be injected in each iteration. So this GF will have some randomness associated to F. It should at least have this property that if somehow magically theta k was already from the distribution pi, then theta k plus 1 should continue to be from that distribution. So that's an invariant. So whatever this proposal step is, you would like that it preserves the target density function. Okay? Unfortunately, it is, I mean, so I mean, I don't know of pretty much any method which can do it, and I'm going to talk about one method which will allow me to do it, but at least in this paradigm, which is a very influential paradigm, there doesn't seem to be kind of a good way to just update. You go from one point to another point, and at the same time ensure that you are preserving the invariant distribution. So there is this accept reject say. Okay? So I don't think I have written it down, so let me just, so you are at some point theta k plus 1, you have theta k, And roughly the accept reject state step looks like you compute the ratio. And I will probably not get this right. There are real experts in this room who will correct me. Hurry, probably the ratio goes in which direction, but it goes in one of these directions. So you compute the ratio and you compare it with 1, and you accept if it's smaller than 1. And to compute this, so what is really the problem in sampling from this distribution? The problem in sampling from pi theta is that this thing is, if you write it exactly, it's this divided by the integral of. And the difficulty is in computing this integral or the partition function. It's not just, so this is, so there's a proportional sign here. So if you also somehow gave me magically the ability to compute this partition function, then there's nothing to do here, pretty much. But in many cases, you can show that these two problems are equivalent. Computing the partition function is equivalent to sampling, and this is a very predominant result in theoretical computer science, which has been used to compute volume of convex bodies and so on. So since we can't, so let's call this Z. So we can't compute this, but the really clever idea of this MC plus Metropolis is that you don't have to, because if you take the ratio of the two probabilities, this is the probability that you are at theta k, and this is the probability that you are at theta k plus 1. In the ratio, the normalizing constant or the partition function cancels out. So to compute the ratio, you just have to query the function at 2 points, at theta k and theta k plus 1. Look at the difference, compare it with 1. If it's more than 1, reject. Don't do anything. Stay at that point, go back to the proposal step. If it's less than 1, accept. Move to this new point and repeat.
What is the use of G?
So, yeah, so what is the use of G? So what is it? Yeah, so that's a good question. So it could be the following, for instance. So I mean, G could be anything. For example, it could be the following. So let's say that this f was really just a uniform function. So then G could be, you are at this point, you take a ball around this point of some radius, and you go to a random point in this ball. It could be something more complicated. For example, you could look at the function f, you can look at the Hessian of this function f, let's say it's a convex function. So that gives you an ellipsoid around this point, corresponding to the Hessian, and then you can move to a random point in this ellipsoid. So it is injecting randomness. The goal of that step is to move fast, take big steps. You want to take big steps, jump around the space. But if you want to preserve the density function, we don't know of a good way to do this. Like you cannot just say that, at this point, take a ball, jump at a random point, It's not going to work, because why should the invariant measure of this random walk be this thing? So the difficulty arises that if you really want to sample from this, then you also have to prove that this measure is an invariant measure of your Markov chain. And the beauty of this Metropolis filter step, which is this accept, reject, very simple thing, is it allows you to prove this in 2 lines. That if first you propose and then you accept or reject based on the ratio, first, that you can compute this ratio without knowing the normalizing constant, and second, that it gives you the right density function. Okay? I'm not giving a lot of details about this because this is not a talk about this, but because I see some people who are physicists, so I'm going a little bit slow. So be patient with me, I'll get to the real thing. The problem with this method is exactly this step. It slows it down. If the function is changing quite rapidly, then you will keep rejecting. You'll reject a lot and you will not move much. So people have studied this, a lot. Let me just kind of now pin down this function a little bit more. So far it seems like it's going to be fully general. It's not going to be fully general. It's going to be, the function f is going to be convex, which means that this density function will be log concave. What that means is that you take the log of the density function, it's a concave function. Why? Because it's a negative of a convex function, so it's log concave. So anything I'm saying here applies to log concave measures. And for different choices of this GF, you get different types of methods. I'm not going to be able to go into these methods, but what I'm interested in this understanding is that suppose not only is the function convex, it's also well conditioned. And what that means is, so suppose it's a smooth function, which means that it has, let's say, the Hessian exists at every point, and the Hessian is positive definite because the function is convex, or positive semi-definite. But suppose you also know that the smallest eigenvalue of the Hessian and the largest eigenvalue of the Hessian are bounded. In fact, they are within some constant of each other. So locally, the geometry induced by this function is well conditioned. So that's the thing that, for this talk, I'm just going to, we can give bounds which also very explicitly tell you what the dependence on the condition number is. But going back to the applications to these images and stuff that I talked about, logistic regression, this is usually okay. What we really want to focus on is D, the dependence of the running time on D. And what do I mean by that? How many calls to the gradient oracle or the function oracle do you make before you get, let's say, 0.01 close in some metric, let's say total variation metric, total variation distance to the target density function. So it has a very, very long history, some beautiful work, but this is the limit of these methods, root D. I'm just focusing on the dependence on D. The condition number and other things also play a role, and so it's the landscape is a bit more. Yeah, sure, yeah. No, please ask questions. This is supposed to be a very interactive talk. That's right, yes.
Usually if you have a Lanchman problem, so for example, I would say that G of f would be something like gradient of f.
Yes, yes.
That plus some noise term.
So it could be an unbiased estimator of the gradient, for instance. So you compute the gradient, it's a vector. And what you can then do is define a random variable whose expectation is this vector. You need to inject some randomness because, otherwise it becomes a deterministic process. Yes. Yeah, so that's this Langevin thing. So there are various versions of this, unadjusted, adjusted, undamped. It's a whole thing. Yeah. Yeah. Even then, this is the best you can get from that. Yeah. Even in the well-conditioned case. Yeah. That's right. We're not even talking about non-convex landscapes. Yeah. So why am I talking about this beyond? So anybody who has taken a course in optimization knows that if you were to optimize a convex function which is well conditioned like this, you don't have any dependence on D. You can give methods which are what are called dimension-free methods. And this is the reason why people use optimization, because it's super fast. Even though this is the problem that makes more sense, because this is more robust. But we don't have algorithms to do this. And that is the big thrust of this work. The big question here is, can we do dimension-free sampling? Can we come up with running time for sampling from these kinds of density functions, even in these seemingly benign settings where the dependence on D is negligible or even independent? That's the big question that we are going to address. And for a very, very long time, I mean, root D was the best. Except there is this method which was developed in the 80s by some physicists, I believe, called the Hamiltonian Monte Carlo. So let me just tell you what the algorithm is first. And then I can tell you why it is interesting. So it starts off by saying, look, you have this function f, which is defined in this space theta. Why don't you do the following? Introduce additional variables. Think of them as velocity or momentum. I mean, in this talk, we're not going to distinguish between momentum and velocity because there's really no mass. I mean, you can fix the mass. So I'll probably use these terms interchangeably. And then define this object called the Hamiltonian. It's the simplest possible setting. You can make it much more interesting. But let's look at the simplest. So this thing then corresponds to some kind of a potential energy. This thing corresponds to kinetic energy. And here's the algorithm. It does the following. In the ith iteration, it picks a random velocity. What do I mean by random velocity? It picks a vector which is distributed according to the normal distribution with identity covariance matrix and zero mean. Everybody knows what this is. And then simulate Hamiltonian dynamics, which is a deterministic dynamics. The equations are here, and we will talk about this. So it's not super important that you parse all these equations right at this moment. Just be patient. Focus on the big picture. So what do? Here's a particle. Here's what I'm doing. I'm kicking it with a random velocity. It lives in a potential well. I let it move deterministically for some time. This t in continuous time. I stop it. I kick it again. This is the algorithm. Unlike the MCMC method with the metropolis filter, the beautiful fact about this algorithm, which is really surprising, and it uses all the aspects of Hamiltonian dynamics, is you can prove that the invariant distribution of this Markov chain is exactly e to the minus Hamiltonian. The Hamiltonian is a function of both the position, which is theta, and the velocity, which is v. So it splits because right now the Hamiltonian that I have defined, the potential energy and kinetic energy don't interact. So you can just split it into two. It's a product of this. And so if you could sample from this distribution, or if you could do something like this, then after some time you just ignore the velocity and just output the position because it has the right marginal. You can see that. E to the minus f theta was what you're looking for. You shouldn't believe this algorithm. And in fact, in this talk, my only goal is to convince you that this algorithm is correct. To prove bounds on this is another 50 pages of work, which I'm going to give some intuition, but yeah.
Any control on the mixing time?
We'll come to that. So I'm going to give you some bound.
It could be huge in high dimension.
It could be huge, yeah. Very, very good point. But the reason why I'm talking about this is exactly to address that beyond d to the half question. The punchline is that we can prove d to the 1/4, assuming some regularity conditions. Okay, so we can go beyond root d using this. But this is not an algorithm. How many people think this is an algorithm here? All the physicists will raise their hands. Any computer scientists think this is an algorithm? Yeah, how do you simulate these differential equations? Discretize them. But then you might lose these nice properties. Yeah, so Spenta has taught me all this stuff, so so it's not, yeah, so this is a staged conversation. Yeah. So there is this, there are these discretization methods. So you might think, oh, this is a continuous time thing, fine. Let's, we all, so I'm from this, engineering IIT background. We do Euler discretization, let's just do that. It turns out that there are this, not just this part is surprising, even this part is surprising to me, that there are some pretty interesting ways to discretize these differential equations, which are called symplectic integrators or leapfrog integrators, which even though do not preserve continuous trajectories, they preserve things like we're going to see in the next slide. Okay? You don't have to, please don't focus on this. Yeah, I mean, this talk is conceptual. We will not need to know much about this, maybe towards the end. So, my goal would be to show you that this is even a reasonable thing to do. And then give you some very high level idea of what the proof might look like. Okay, so this method is actually very widely used in practice. This is a method, but the questions about what is eta, what is t, how to set these things, this is what I call parameter tuning, right? People just do it without much, what to say. I mean, yes, yeah, there are people who can use these things without, can specialize these, but we want to develop a theory for this because then we get a principled way to set these parameters. So there's a conjecture, I wouldn't call it a conjecture, it's some kind of an informal conjecture, which basically said that if the Hessian of this function is smooth enough, if the Hessian of this function is not changing, then this leapfrog integrator requires only d to the 1/4 gradient calls to sample from, when I say one smooth, one strongly, well, maybe some typo here. Yeah. So this should be order 1. So, yeah. So it means that for well-conditioned density functions, that's the right answer. So that maybe addresses your question. This is why we are even talking about it. And let me just tell you something which I'm not going to mention any further, is that there are variants of this where you can get it to 1/2k or something like that, and by assuming some kth order smoothness conditions on the function. So really, if you have a method which takes d to the 1/k iterations, and if you set k to be something like log d, then this is really becoming dimension independent. Okay? It has more assumptions, more than just your assumption on the second order or third order smoothness. It'll have a kind of log dth order smoothness. So, and I guess this is why these methods are used, because in the real world data, you probably have some of these properties. But what are these smoothness conditions precisely anyways? So that's why I say this is an informal conjecture, because it's not even precise, like what do we need to assume to prove this bound. So the hard part of this conjecture was even to formulate this conjecture, the precise regularity conditions that you need on the functions for this conjecture to hold. Okay? So this is, now let me show you some pictures, and then I'll probably mention the result. So once again, so these contours correspond to the level sets of this convex function f. And so the algorithm is really what I just described. You have a ball or a particle. Theta is its position space. The vector v is velocity space. Together, theta and v are called the phase space in physics. And so here's what you do. You impart a random velocity, which in this case is just easy to sample from a Gaussian distribution. Let it move according to the laws of physics deterministically for some time. Stop it. Give it a random velocity again. Let it move. And yeah, this is. So if you could simulate these differential equations exactly, if you could do that, then yeah, so then this would be an amazing algorithm, as you will just see. Okay, is the algorithm clear? So at least there's one take home. Maybe many people here learned a new algorithm. So what did we prove? So this is
Like what we call multilayer dynamics, but you choose the velocities randomly from a point.
yeah. So this, I mean, yeah. So
The dynamics is where you have this.
that's right. Yes.
Initially just let it run forever.
Yes.
But now you are resetting the velocity.
I'm resetting the velocity for a very good reason, actually, as you will see. In fact, yeah, I'll come to that. So I think I already claimed, and I'm going to show a proof that the target density function is an invariant distribution of this dynamics. It will actually turn out to be the case that this refreshing velocity step is not even necessary for that. You can prove that the target density function is an invariant of this continuous deterministic dynamics. So why am I doing this refreshing step anyway? Anybody has an idea here? And when you want to prove a mixing time bound on a Markov chain, you need two things, right? So you need, the first thing is ergodicity. I mean, yes, the distribution that you're looking for is invariant, but you're not going to be starting from that distribution. You're going to be starting from some arbitrary thing. So you have to converge to that. So that is really the reason why the random step is even there. Okay? So we proved, so this is joint work with my postdoc who is now a faculty, that the Hamiltonian Monte Carlo algorithm with this Leapfrog or symplectic integrator essentially verifies or confirms this Creutz's conjecture. So the d to the 1/4 you can prove. And this is a proof like a proof, I mean, I shouldn't be saying things like this, but since there are, I mean, so just, there's a mixed audience here, so these are mathematical proofs. Rigorous proofs, okay? So let me state the theorem. It's going to be a little bit ugly, the next few sentences, but I have to make it more precise what this regularity condition really is. Okay? So the first condition is more benign. I mean, this is just saying that the function is strongly convex. This 1/10 can be, and 10 can be replaced by any constant or even non-constant. We can get bounds which are explicitly and mildly dependent on this condition number. But here is a more interesting condition, which says, so even Creutz kind of knew that the Hessian has to be smooth. The Hessian cannot change a lot if this method has to work. Okay? And I guess the reason for, maybe I can go back a few slides and just point. So if I look at this thing here, the difference of the gradient at the new point versus the difference of the gradient at the old point. You can ignore all of this stuff, but this thing really behaves like the Hessian. So the error in these numerical trajectories is controlled by the variance in the Hessian. Okay? you have to believe me on that one. I mean, I don't think I can go into these calculations. So you need some regularity conditions on the Hessian. The question is, what are these regularity conditions? And the regularity conditions that we have are the following. It looks a bit strange, and so I'll give you an example. So the conditions say that there are some directions, x1 to xr. So these are some directions, not necessarily orthogonal, in unit vectors. So this is the unit sphere. And the Hessian satisfies the following. That if you perturb the Hessian, if you go from θ1 to θ2, and you look at how the norm of the Hessian changes, the 2 norm, it is bounded by some constant times the infinity norm of these 2 strange objects. So what is this thing anyway? So this matrix X is basically, you have organized all the columns. So this matrix X corresponds to a D cross R matrix where each column is this vector. So you're looking at the infinity norm of the displacement vector with respect to these directions. So you're given x1, x2, xr. And the condition says that as long as the Hessian is smooth or has a small Lipschitz constant with respect to a set of random vectors, then we can get a bound which grows like d to the 1/4 and also the square root of L infinity. And now comes some of the other stuff which I have so far ignored, the epsilon. So what is the epsilon? Well, at the end of the day, you're going to output a sample from some distribution. So epsilon is a measure of closeness to this distribution, and the measure that we have is the Wasserstein 2 metric. Okay, whatever that means. It's just some way to measure distances between probability distributions. So this is the theorem. It's an informal version, but yeah. So you can ignore this for a moment and just let's go back to the application I mentioned in the first slide, which is this logistic function, which shows up in machine learning a lot.
So,
yeah.
in high dimension, it happens very often that the Lipschitz constant depends on the dimension.
That's right. That's right. Yes. Yes. Yes, that's right. In fact, yes. So we can do a precise computation for some. Yeah, so you have to do a precise computation. So this can be misleading, and that's what he's pointing out, that this number could be D. And then, this is not a D to the 1/4 algorithm. So this is a very abstract theorem. As such, it has no utility because so the nature of this theorem is the following, and this is a popular trend in machine learning these days. You have an optimization or a sampling problem, you say, if I assume such and such things about the geometry of the function, then I can show that the method works. But the question is, how can you assume such and such thing about the geometry of the function anyways? And this is where the next thing comes in, that this geometry is a function of data at the end of the day, because these functions encode data. So somehow you have to show how these conditions can arise from some conditions on data. And this is, not many people are actually doing this in optimization still. But this is what one should be doing. That you say, okay, I have some very specific results I'm referring to. I don't want to name people, but you should be showing things like this, that you have some specific function which is derived from data. So xi's are data vectors. And so roughly, in our case, it turns out that if you had this logistic ridge regression function, then this L infinity is precisely this thing, which is so xi's are unit vectors, so these are data vectors which come from the sphere. And what I'm looking at is kind of what I'm calling coherence. It's not a standard term, but let me just call it coherence. And then you can do this calculation now. You can actually calculate what this is. So this turns out to be, I don't remember exactly, but maybe d to the 1/8 or something like that. So you don't get d to the 1/4, but you still get something better than d to the half. Yeah.
Do the MCMC algorithms also have an inverse polynomial dependence on epsilon?
Very good question. So the MCMC plus Metropolis have a logarithmic dependence on over epsilon. Yes. But let me just kind of go back and yes, so there it's not the same thing. Yes. Good point. But you can construct versions of this with logarithmic dependence. It's much more involved, and that's a follow-up paper I have. Yeah. Any more questions? Yeah.
Hessian is some sort of a random matrix.
No. Hessian at a random point is a random matrix, yes. So, I mean, Hessian at a point. Hessian is not as such, I mean, Hessian of the function f, but you're evaluating it at a random point theta. Yeah. It can't, right? Because we know that at any point, for every theta, the determinant is at least the determinant of this identity by 10.
Using your assumptions to be able to prove something, they may not be valid, right?
They may not be valid, yes, but we prove that for these kinds of things, they are valid, yeah. So if you have some so here is the thing, right? So you have some distribution on data that gives rise to some geometry. We have to prove that, and that geometry is enough for us to prove or apply our theorem. Yeah. Okay, I think I think this gives you a flavor of what the thing is. I don't expect you to just look at it and understand what this is. I mean, like, or why this is true. So let's go back to Hamiltonian Monte Carlo, which I think is a beautiful algorithm, and let's try to prove that in the continuous time version of Hamiltonian Monte Carlo, the target density function is invariant. This is the essence of this talk. I don't think I will go into the proof of my theorem. And this is something I didn't prove. So this is, but this is where the physics and machine learning meet. Okay, so let's review a little bit of Hamiltonian dynamics. So the setting is that you have a particle which has a position space theta and a velocity or momentum space v, indexed by time or parameterized by time, and this is all classical physics. So and you can define an Hamiltonian. Here I have chosen a very simple Hamiltonian, which is f theta plus half v square. This is just a 2 norm. You could make it more interesting, and then the algorithm is still valid. It's just called the Riemannian version of HMC, Hamiltonian Monte Carlo. You could associate a geometry, a metric, and then look at the norm with respect to that metric. You could do all this, and these are all valid algorithms, so it's not, and people use it, so. But let's not bring in Riemannian geometry in this talk. Let's just focus on this simple Hamilton. So what do Hamilton's equations? So Hamilton's equations are really the left-hand side here. So it says that the rate of change of position is the partial derivative of the Hamiltonian with respect to the momentum or velocity. Once you write down the Hamiltonian, this tells you how the position changes, and this tells you how the velocity changes. The rate of change of velocity is the negative partial derivative of the Hamiltonian with respect to the position. Okay? It already has this symplectic structure built in. I mean, that's this identity minus identity, the skew symmetric form, for those of you who you know. In this very simple setting where I choose this Hamiltonian to be just potential energy plus kinetic energy, This is nothing more than Newton's laws, right? Because what is this saying? It's just saying that the rate of change of position is the velocity, and the rate of change of velocity is the force, which is, acceleration, which is the force. I mean, mass is 1, the negative derivative of the potential. It's a very simple setting. So, classical mechanics, the properties of these trajectories. One, it's time reversible. What does that mean? I probably don't even write it down what it means, yeah. So what does it mean? It means the following. Suppose you start a particle at a position theta with some velocity v, theta 0 and v 0. And you move it according to this Hamiltonian dynamics. You stop it after any time t. You look at theta t and vt. This is your position and velocity. Now you reverse the velocity. So you start at theta t with negative vt velocity. You will trace back exactly the same path. You will arrive at theta 0 with negative v0 velocity. That's time reversibility. All classical mechanics has to satisfy this. Okay? That's one property. Second property, which I guess is probably the most obvious one, is that the Hamiltonian, because this is not a time-varying Hamiltonian. This is a time-independent Hamiltonian, and so the rate of change of Hamiltonian with respect to time, dh by dt, is 0. You just check that. Use the chain rule of derivatives, plug in the partial h by partial theta I, which is minus dv by dt, and this will all be just 0. This is completely trivial. So, Hamiltonian trajectories preserve Hamiltonian. This is Liouville's theorem, right? Yes? I mean, it's Liouville's theorem, yeah. This is the first invariant. Something that perhaps I don't expect many people to just discover, if you're seeing it for the first time, is the fact that it preserves volume. This is a very interesting thing. Let me explain this to you. Well, this is Liouville's theorem. Okay. So what this is saying is the following. So the particle lives in Rd cross Rd, so which is this space, and you look at some volume element in this. And here is what you do. You take each point and you move it according to the Hamiltonian dynamics for the same amount of time for each of this. Okay? So at the end of it, you may get a different set. You will get a different set, which is again a volume element. Trajectories are not colliding, so it's time reversible. So trajectories are not colliding. So you will get a volume element. If you start with a non-zero volume, you will get a non-zero volume thing here. That property says that the volume is preserved. So the volume of this is equal to the volume of this. Once you know what to prove, it's not too difficult to prove. You just compute the divergence of the following vector field. At every point in Rd cross Rd, you associate the Hamiltonian vector field. And now you just compute the divergence. I'm sure we all did this. I did this. I never remembered this until I had to use it, what the divergence is. But I'm not a physicist, so Spenta is smiling. But yeah, that's true. We learn a lot of things unless we use it, we don't know what it means. So look at the divergence, it's just 0. It follows from, again, some kind of, so here is what can happen and here is what does happen, that if you just look at the volume element that I drew restricted to the position space, the volume can fluctuate massively. Just the velocity, if you restrict it to the velocity space, the volume can fluctuate. But together it can't. And all this stuff holds very, very generally. And this is You know, in this whole area of symplectic geometry, it attempts to generalize Hamiltonian dynamics on manifolds, and this pretty interesting mathematical physics behind it. Okay, any questions about this? Yes? No. It doesn't. If it holds when the Hamiltonian also is time dependent. No. Yeah. Volume is preserved, but this, I mean, yeah. Because you will have to then take the time derivative of the Hamiltonian as well. So that's like adding friction or something like that. If you add friction, right, then the Hamiltonian starts depending on time.
Is volume just volume, or is there some other sort of?
No, it's just it's RD cross RD endowed with the Lebesgue measure. You're looking at a measurable set, it's the volume of that. Yeah. On general manifolds, you have to define a base measure, which may not exist. So you can only work over manifolds where you can define measures. Yeah. But we are just on RD cross RD right now. Yeah. Well, I have not yet gone to the point where it gives the correct measure. I'm just still enumerating the properties of Hamiltonian dynamics. In the next slide, I'm going to show you why the measure is invariant. Yes?
The question is, does volume have a physical meaning, like Hamiltonian has a physical meaning, like energy?
There are far more knowledgeable people in this room. I will let them answer this question. Does the volume have a physical meaning? The volume in the phase space. That's Praneeth's question. Is entropy? Okay. Can you speak a bit loudly? I mean?
The log of the volume will be given.
Okay. That's a definition of entropy here. Or you give that, you associate that meaning. Log, yeah. So roughly, what he's saying is that the log of the volume, you can think of it as entropy. Yeah. I mean, volume is some kind of a determinant, so this is log det of something. So I think that's something you find more comfortable. Yeah, log det is, you can think of it as an entropy or something. Okay. Let's see. Let me give you a sketch of the proof of correctness of this continuous time HMC. And we will use all of these three steps: time reversibility, energy preserving, and volume preserving in the phase space. So there were two steps in the Hamiltonian Monte Carlo chain, if you recall. The first step was to pick a random velocity vector from the normal distribution. And the second step was this deterministic. So what we're going to show is that in each of these steps, the invariant measure e to the minus h, where h is the Hamiltonian, is preserved. The easy part is the refreshing velocity part. So what does that mean? So you were at some point theta. So let's say you were at a point theta with some velocity v, and I promised to you that this theta and v were given to you as a sample from e to the minus h theta v, that density function. Okay? And now I'm changing this v to some v prime, right? But my Hamiltonian, at least the one I chose, has this form that it is separable. So e to the minus h theta v is just the product of e to the minus f theta v times e to the minus half v square. So its marginal is already the normal distribution. So the marginal of, so I'm saying something very trivial, that the Hamiltonian that I defined, its marginal with respect to the velocity is the normal distribution, And in fact, that is the reason why I chose the normal distribution to refresh it. Were you working in some Riemannian manifold where this thing would depend on the position? Then you would have to replace it with that. You would have to sample a vector from that distribution. So, yeah, so all I'm doing is, I had a sample from the invariant, so this is what we want to prove, okay? That if I give you a sample from the invariant distribution, from the right distribution, then the steps of the Markov chain don't destroy that property. They will certainly change the point and the velocity. But it will still be true that the new point and the new velocity will be as if I gave you a sample from the original density function. That's what it means, okay? So I'm just changing the velocity with a random unit vector drawn from the normal distribution. Yes, the velocity changes, but overall the distribution is still the same. So you don't need, the only thing you need is that the reason why we chose the normal distribution is because the choice of the Hamiltonian. If you chose something different, you would have to do something different. But then your computational task of sampling from that distribution will also increase. Keep that in mind. Because we are focused on algorithms here. So you can choose a very complicated metric and define the kinetic energy with respect to that. But then you also have to give me an algorithm to sample that velocity. Okay, the second part, the deterministic part. Why should that preserve the invariant measure? And here's the reason. So this is a sketch of a proof, but you can make it formal. So you have this space. You partition them into volume elements, cubes, let's say, infinitesimal cubes, and pick one such cube. They're so tiny that the Hamiltonian is basically constant in this cube. Okay? And so you pick a point in this cube and the Hamiltonian is just as theta v. It's constant in the entire cube. Just pick these so small. So the probability of you being in this, if you were to sample from the invariant measure, was this. The volume, this is the Lebesgue volume, times, is proportional to this, times this. Okay, I'm not saying anything very deep. I mean, this is how you would prove that invariance property anyways. Now I have to show that when I apply Hamiltonian dynamics or look at the flow, Hamiltonian flow on this cube, and I get to a new thing that has the exact same measure. So here is where I will use all three of the facts that I mentioned: time reversibility, energy preserving, and volume preserving in the phase space. So if I start at theta v and go for some time, I know that the Hamiltonian is preserved. So this number doesn't change, right? This C is anyway, remember we are chopping up the phase space. We're not chopping up the position of the momentum, we're chopping up the phase space. So that also doesn't change. So the only bad thing that can happen is that somehow trajectories collide and you lose volume, but that's also not going to happen. So all of these three things, time reversibility, the fact that the Hamiltonian is not changing, and the fact that the volume is not changing, gives you can make this rigorous. Sorry?
Time reversibility actually gives you immediate balance.
Detail balance, yeah.
And without that, you just get the next stage.
Yeah. So
Time reversibility.
where is time reversibility used? So how would you, formalize this, right? So you say, okay, you want to show that the volume, so you chopped up the space, right? And now to each of these small cubes, you apply the Hamiltonian flow. And you kind of want to make sure that because, trajectories are not colliding with each other, you again get a chopping of the space. Not necessarily as cubes, but as something different. Roughly that's where you would use. I'm sorry? Yeah, it could, right? Yeah. Yeah, no, that's a good point, right? So the first thing to check is that it preserves your target density function, which it does, but it may also preserve other things. This may not be the unique invariant measure. That's what you're asking. Yeah, that's a valid point. Yeah. Yeah, so that is. So now, if you look at it, why do you need this step? The reason is that, so imagine, maybe one way to think about it, maybe not entirely correct, is like you're on a billiard table, right? You hit a ball. If you choose the wrong angle, then it will just keep going around. It's not ergodic. It will not fill the entire billiard table. So, but from time to, if from time to time you stop it and then hit it in a random direction, then you will start filling up the whole thing. Yeah. I change it? Change its knob? Yes, you could. Because you're sampling from the normal distribution, you're sampling from the sphere. That's right. But no. So this argument is different, right? So here, so in this step, we are not changing. Yeah. So theta and v are changing, but so yes, the norm of the v is changing. Theta is also changing as you're following continuous time Hamiltonian trajectory, but the Hamiltonian is not changing. The volume is. Oh, but then I use this argument here. So there are two steps in my Markov chain, right? So this is a deterministic step. So the invariance of this step comes from this argument. This is where the physics is used. Here, no physics is used. Here, this is just saying that the choice of the velocity vector is just the marginal, right marginal. So, this is what you would do. But this step lets you achieve ergodicity. I'm not going to go into details of this, but yeah, the geometric ergodicity you can get from this. So if you do this enough number of times, then pretty much the only thing that will get preserved is the e to the minus h. That's what you, yeah, maybe it's a good thing I am not that much of a physicist, because I am convinced by this proof. But we can talk offline. I'm sure you're saying something interesting, but yeah, this thing can be made fully formal mathematically. But okay, so I have a theoretical computer science background. So this problem lies, we study this problem. Volume computation, sampling from convex body, sampling from log concave function. This is problem we study in theoretical computer science. But this algorithm is just so out there. I don't think anybody in theoretical computer science, at least Hari is one of the experts in this. Did you know this algorithm? In machine learning, it has been around, but if you wear your TCS hat, you were at some point TCS, or still are TCS. I will stop. These slides are very configurable. Stop at any time. Yeah, no, I have my, yeah. I don't think I'm going to go in the second part, or maybe I will just show you what it is. Yeah. I think for me it's better if people understand one idea than I give like multiple things and they don't understand anything. So, yeah. Okay, so let me tell you now some intuition as to why this will have any hope of getting good bounds, better bounds than the previous. And this is a crucial argument. So the mixing time bounds are proved using a coupling argument. So what's coupling? You will couple two chains of the Markov chain. One will ideally start from stationary and invariant distribution, one will start from arbitrary point, and you want to prove that in one step of the Markov chain, there is contraction in some distance. Okay? And that is the key observation. It takes, this is not a trivial thing. I don't think I can prove this to you. Instantaneously, it is true. You can prove that the instantaneous vector fields are such that they are not pointing outwards, they are pointing inwards. So you can make this precise using differential geometry. But I'm not going to do that. I'm going to show you an example. But here is the thing you can prove. So what's the coupling in this case? So the coupling is actually the most natural coupling, that you start at two different positions, but you give them the same velocity. Okay? So okay, maybe I should have not said what I said before. I should have first shown you this picture and then said. Now how many people here believe that these two particles will come close instantaneously? For a moment, they will come close. So they do come close instantaneously. That's fine. That's of mathematical utility. You want to prove that they will keep coming close for a very long time, which doesn't depend upon the dimension at all. And you can prove that. This is, so Hamiltonian trajectories for strongly convex potentials will contract for time which is independent of the dimension. This is the hope. This is the result. Once you prove this, you know that you can get down to as small time as you want, potentially. If you don't believe me, here's an exercise. Okay, this is the simplest potential. I mean, this is just a quadratic form, which is diagonal. The condition number just means that all CIs are between, let's say, 1/10 and 10. And you can write a closed form solution for this and check. If you don't believe this, then I'll show you the next slide. Well, first of all, this is all in continuous time. So when you start discretizing trajectories, you might lose that. But yeah, I mean, in total variation, you can get from this one. On what? So this is a theorem. I mean, it's pretty precise. Huh? No. I mean, the Hamiltonian, the potential function is strongly convex with constant condition number. So this thing just depends, this is independent of D, but it depends on the condition number. And what we can prove is quadratic dependence on the condition number. So Lee and Vempala actually improved this recently to just the condition number. And you need a condition number dependence that comes out from this example already. So you can show that this will contract, and I'm going to show you the pendulum example, which is just this, that these trajectories will contract basically for time, which is something like 1 minus 1 over the condition number.
The contract is the Euclidean norm, so you get false time.
That's right, yeah. Yeah, so I'm not going into a lot of mathematical details because I want to focus more on the idea. So here is the setup, right? There are two pendulums, okay? There are two pendulum at two different positions. You give them the same velocity. They will come close. It doesn't feel like that, but they will come close for some time. And the algorithm does exactly this. It knows for how long it's going to come close and stops it at that point, and then refreshes the velocity. and they come closer, then they come closer, and eventually they collide. This is the algorithm. So I need an estimate on what, some kind of a bound on how long these two pendulums are going to come close. My goal is to collide these two pendulums, to bring them to the same point. If I just let them run, I guess we all can imagine this. They will maybe, yes, I mean, maybe if you have never thought of this, you will not even believe me that the pendulum come close. But they do come close, but then they will go far and then they will swing, right? So you have to stop them at the point where they start diverging. Stop them. At that point, you couple them again with the same velocity. That is the reason why we are refreshing velocity in this algorithm. Okay? And that is why we need some bound on the contraction time, because then that tells us how long to run this Hamiltonian trajectory. So I'll show you this thing. I think this video, I don't know if it's working. Yeah, it's working. You see, I mean, these things are plotting. But I mean, yeah, I guess this is just for people who don't believe me. But yeah, I mean, you see that there's an oscillatory behavior, so clearly they don't keep coming close all the time. They will go far. So you need to stop them at a point where they start diverging. And that's the basic structure of the proof. It's a coupling argument, and the contraction being independent in the continuous case tells you for how long to run it in the continuous time, and then there's this whole issue about discretization, which I think I'm gonna, yeah, maybe I'm gonna skip, but yeah, I just want to say one thing, that this is what is called the symplectic or the Leapfrog Integrator. Even though this is a discretization, it preserves the volume. And so the reason why the dimension comes back into this is very different from the Metropolis MCMC. It's a completely different reason why the dimension dependence comes back, even though in the continuous time there is no dimension dependence. So that argument I showed to you, or at least hinted in the previous slides, is enough to prove that if you can simulate continuous time trajectories, you'll have no dimension dependence. And now it's about discretizing things and making regularity assumptions so that, yeah, so it's a very different reason why the dimension comes back. So, yeah. But maybe I give you some intuition why the standard Euclidean Lipschitz Hessian condition, for somebody who's an optimization, they know these things very well. These are like self-concordance conditions in interior point methods. Why these are not enough. So the most naive thing to do would be to assume that the Hessian is Lipschitz with respect to the 2 norm. So H is the Hessian of the function. And you have to believe me on this one. I've said it a few times that the numerical error is controlled by something like this. So you are at theta, you take a eta step with velocity. So V was a velocity, so if you take a eta step, this is what your new position is going to be. So you have to compare the difference of the two Hessians applied to the velocity. This is just a scaling factor, but it's kind of important here. And so suppose you had this property that the Euclidean, the Hessian is Lipschitz with respect to the Euclidean norm in this precise sense. I claim that this is not going to bring you below root D. In fact, this doesn't even work for the normal Gaussian, when F is just a Gaussian. The reason is that this gives you a bound like this. I know that from the invariant distribution, right, if you sample V from the invariant distribution, it's distributed exactly like this. Its norm is something like root D, right? And So if I want this number to be small, I would like to set eta to be something like 1 over root t. But that means that since each phase is discretized at a rate of eta, this means that in each phase you're losing root d iterations. So this will not work. And that's why going back, I said it's an informal conjecture. I said, yeah, if the Hessian is smooth, but what does it mean the Hessian is smooth? In this sense, it is just not possible. The conjecture is not true. So that is where this other thing comes up. This is what we define. This is a norm that we look at. And in this norm, the positive thing is that if you pick a random Gaussian vector, look at the infinity norm, it's root log d. Okay? The bad thing is that, as I think you pointed out, that this L infinity could be large unless the function is separable. This is a useful case. It's not a useless case. The function is separable. But we want to do something more than separable. And so that's where the idea of transforming the norm to align with the data vectors comes in. And this kind of heuristic reasoning leads us to our notion of the regularity condition, which when combined with these continuous idealized proofs gives us our result. Okay. Yes. I have to wrap up in 2 minutes. I think I don't want to start a new story. I'm just going to conclude. This is a pictorial view. I can spend 30 seconds on this. These are the data vectors. The thing is that I know, because of the way we have chosen the Hamiltonian, that the velocity, if you were to pick from the invariant distribution, it will be a Gaussian vector, and there I know that the correlation with any fixed vector is small. And that's what saves us. It's much, much smaller than the 2 norm of this vector. This thing is like root d. This thing is like log d. Okay, then you can do induction, and this is the proof. Okay, I'm gonna skip this. This is more statistical physics, but something about non-convex optimization. Okay, let's just conclude in the 1 minute I have. So I'm somewhat new to this, using physics to think about optimization and sampling, but from whatever I have seen so far, in fact, now I realize that many of my recent works have this theme implicitly or explicitly, that they are using algorithms inspired from physics. Even take biological creatures into account, which are also following certain differential equations. And the nice thing that kind of comes out is that there's this can lead to rigorous algorithm design, which is useful in theoretical computer science. It can help you tune parameters. Once you have these bounds, guarantees, it can help you tune parameters, identify the right potential functions. Once you have a physical interpretation, as you said, like the volume is, you can think of it as entropy, there is energy. These are, or some combinations of these end up being good potential functions for you. So you can gain a lot of intuition. This is not a prescriptive methodology by any means, okay? But there is usefulness in studying physics, especially, or at least classical physics, especially if you are interested in algorithm design. There are other results which fall in this kind of line of work. The one which I just zoomed you past, which appeared in court last year, and there is a whole bunch of other stuff, including a problem which is central in theoretical computer science, which is sampling from polytopes. So using some of these ideas, we can get the fastest known algorithms for, at least in some settings, for sampling for polytopes. So I think I'm going to end here exactly at 00.00. Thank you for your attention.